controller worksheet, the engineering notebook, outreach notebook, and business plan.
All right, thank you.
So we're FTC team 9794 Wizards.exe based in Rockville, Maryland. So a lot of people ask us about the last part of our name, .exe, and we tell them it's not just a nerdy reference and executable file, but it's actually our mission to engage, expand, and educate the community about first consent.
So even though we're a second-year team, 8 of our 11 members are actually rookies, primarily in 7th and 8th grade. This year we organized ourselves into different sub-teams to work on different aspects of the robot and outreach. And everyone on this team led at least one outreach event and also got an opportunity to help build on the robot. Unfortunately, we had 5 members who weren't able to make it because of magnet high school testing. But I'm Lena, and I'm the project management wizard and engineering network wizard.
I'm Arjun, and I'm in 7th grade, and I'm a robot wizard.
I'm Jyotsna, I'm in 7th grade, and I'm the testing wizard.
I'm Manav, I'm in 7th grade, and I'm an outreach wizard.
I'm Sartuk, I'm in 9th grade, I'm the software wizard.
I'm Ishan, I'm in 9th grade, and I'm the chief executive wizard. And this is our 12th man, wizard, Gandalf. So, at the beginning of the year, we set our priorities for our robot. We decided that we wanted to be able to push both the beacons during autonomous, we wanted to be able to shoot and pick up particles during teleop, and ultimately we wanted to be able to lift the cat ball during endgame. So we followed an iterative design process which included designing, prototyping, setting requirements, and we would have monthly design reviews where mentors from companies would come help us out, and we would share our ideas with them, and they would give us some feedback. We also split our robot up into different sub-teams. So we would have the drivetrain, we also had the particle sweeper, we had the beacon pushers, and we had the shooter. And we did this so that way we could all be working on the robot while at the same time. We also created a system envelope in PTC Creo to help us with our design process.
Since beacon pushing was so important to our team, we tried out 2 different mechanisms. The first is a Lego linkage system, and then our second mechanism is a 3D printed rack and pinion system. This is completely designed by us, and the innovative part about it is that we have a spring mechanism on the end, so then we don't damage the field or our robot. And so here we have a poster board showing the evolution of our 3D printed parts on our robot.
So all of these 3D printed parts, we completely designed on our own, and we completely made them on our own.
Do you mind to take a picture?
Yeah, go ahead.
Since shooting was a big part of this year's game, we created 4 different prototypes for shooting. Our first prototype was a pitching machine with Andy Mark stealth wheels spinning in opposite directions. And our second design was a Lexan flicker.
Yeah, so this was the shooting with 2 wheels, and this was the Lexan flicker.
Our third design was a choo-choo catapult, which is pulled, so this is a catapult pulled back by a choo-choo linkage. And our fourth design was a one-wheel shooter. And so one of the things we really noticed was when we noticed in basketball, players to put backspin on the ball, so if they miss, the ball returns to them. We imitated this. So as you can see, the particles always come back to us because we have backspin with our shooter. So we also did the physics of a one-wheel shooter to determine that we need a 1.85 gear ratio on our motor. And so to fabricate our robot, we've done a lot of 3D printing, and a good example of this is our beacon pushers. We've also done heat forming, which we used to create the curve on our shooter, and we've done machining for all our drivetrain plates and Lexan plates, and all of our team members have learned how to machine parts.
In autonomous, we plan to push both of the beacons, and to detect the colors, we are going to be using our camera on the phone. And we also plan to shoot 2 particles and push the cat ball off of the center vortex and eventually park for a maximum of 100 points. And to do this, we use a total of 5 different sensors for our robot to navigate around the field. So in our autonomous software, we use a state machine opposed to the linear op mode. So this on the laptop is our first state machine diagram. If you look at it, it's kind of crowded, so we had over almost 15 different states, and it started to look more like a linear flow than a state machine. So what we did was we found the methods with common parameters or motions, and then we took those parameters and we built a sequencer, and the sequencer held the states and the parameters. and then the state machine would apply those parameters to move the robot. This way, it was much easier to debug. We wouldn't have to change our state machine. We don't have to change numbers in the array. And also, people who do not know how to program in Java can create autonomous programs because all they do is they have to write names and numbers in the array.
We were able to write our autonomous program in less than 20 minutes using this sequencer.
And also, members on the test team can write their test programs without any help from the software team.
So a unique feature of our teleapp program is we use a frame of reference change. So when driving our Mechanim robot, we had a problem knowing which side was front. So the robot, it was hard for the drivers to tell which side was front. So what we did was we used the Adafruit IMU sensor to change the frame of reference. That way, no matter what orientation, the robot can be rotated in any orientation. Forwards will always be going away from the driver, and backwards will always be going towards the driver. We also use a state machine in teleapp. So it's a very simple state machine that controls the shooter gate. So when the button is pressed, it will open the gate, and automatically after 0.1 seconds, the gate will close, so only one ball goes through. This makes it easy for the drivers to just press a button, and it will shoot one ball.
So this year I'm on the test team, and testing was a good way for the new members on the team, including myself, to learn about the hardware subsystems and software. We did this by creating test files for each individual subsystem. The test files consisted of a short description of the test, a procedure, and a visual, what the test would look like. This is an example of a procedure, and this is an example of the visual that we would make. And when we concluded the test, we would send the results back to the designers.
So first, this had a huge impact to their various programs, and our team tried to have an impact by engaging, expanding, and educating our community. We have over 1,000 outreach overs, have participated in over 70 events, and each one of our team members ran at least, or was the lead on at least one outreach event. In our our outreach notebook, you can find more about the events that we did. And another thing that we tried to do was outreach to every level of FIRST.
So FLL Junior is where it all begins, and our goal was to make 5 to 10 new FLL Junior teams. We accomplished this, and we got 7 new teams started. That is a 5% increase in the FLL Junior community of Maryland. So not only did we start these teams, we also raised funds from Stanley Black & Decker to buy parts for them. In addition, we mentored 3 of them and fostered cooperation through an online community forum and monthly user group meetings. FLL is the next step. Our main theme for FLL outreach was educating, taking what we've learned in our years and giving that knowledge back. So we were able to start 4 new teams and are currently mentoring 5 teams. But what I think was the most impactful was the 11 training sessions that we had, 4 for coaches and 11 for EV3 programming, where we were able to reach over 50 FLL teams. None of this would have been possible without Launch Workplaces, who actually donated us their space to conduct these trainings.
So for First Tech Challenge, our goal was to educate the First Tech Challenge community with our experiences. We held a training for rookie teams at the First Tech Challenge kickoff in Maryland, where we talked to them about how they could have a successful qualifier. We also are mentoring a rookie team, and we have had an autonomous help desk to help other teams with autonomous at one of the FTC events in Maryland. We have partnered with Catalytor Makerspace to run a 3D printing and laser cutting class for FTC teams, and we also have held many social events and are volunteering at an FTC qualifier. Lastly, a team in New York has been Skyping with us and sending us emails, and we've been sharing our ideas and giving each other feedback. For FRC, we have gotten a mentor from the Blair Robot Project FRC team, and she's been helping us with looking at our design and giving us feedback. She's also helped us with fabrication methods and talked to us about how we could better fabricate different components of our robot. We've also volunteered at many different FRC competitions, including the first FRC Chesapeake Regional and the Battle of Baltimore. Lastly, we've been working on our outreach advocacy with the team Body Electric.
Our team has spent a lot of time reaching out to our national, state, and local government officials. In May of this year, we met with our congressman to discuss how we can get more kids involved in STEM programs and how we can get more funding into programs like FIRST inside of schools. And we met with him and his staff to discuss Dean's homework, which was which would raise there was a bill which would raise more funds for FIRST programs. and he agreed to co-sponsor it, and he enjoyed the experience of learning about FIRST.
In addition to connecting with our government officials, we've connected with 19 companies, received 5 grants and 7 additional sponsorships from these companies. We've also received 6 corporate mentors who have attended our monthly design reviews, as well as helped us with robot design. We also are going to go on 2 tours of the companies to learn more about what they do.
So thank you so much for your time, and feel free to ask us any questions.
Wow. Okay. What was your favorite outreach event, personally? Somebody.
I really
Separately.
liked the FLL trainings. We had beginner, intermediate, and advanced. Actually, I can't really pick between those. I liked all of them, especially like how many teams we could reach, and how like each of as soon when they left, they always knew something more than what they came with. And all the things that we were teaching were like really nice principles, and that was probably my favorite.
These beginner, intermediate, and advanced trainings that we ran, they were for teams, and we had 3 weeks in a row. We had teams come in, and you could definitely see growth from the first session to the last session, and it was amazing to see how they use these in competition, because we saw some of them in competition.
Essentially, we made teams who didn't know anything about the EV3 programming to being experts, to being really advanced with the programming.
These training sessions were also open to outsiders at first, so we connected with the FIRST community and our local community.
Could you tell me a little bit more about the autonomous for the beacon?
Alright, so for autonomous, what we do is we use a camera sensor. I don't have it on the robot right now, but it's a phone camera. It goes right here. And we use a library called OpenCV. And what this does is it detects the 2 blobs of the beacon, red and blue, and it can tell us which is on the right of the frame and which is on the left of the frame. Using this, we are able to determine what beacon we need to press, and we have 2 beacon pushers, so we can just stand in front of the beacon and we can just extend one out.
And the thing is, if we go too far, the spring mechanism will so that it's there, so then we don't damage our robot or the beacon.
Okay.
Do you mind if I take a picture of Gandalf?
Go ahead. Probably one
Yeah, not really bad.
So another unique thing that we did in our autonomous program is we use the Adafruit IMU, which is kind of hidden, but what it does is it allows us to keep the same orientation while we're driving. So let's say we want to drive in this direction. Sometimes the robot might slowly swerve. We use the Adafruit IMU to keep us on the same track. So proportionally, the more that we go off, the more it will slow down these wheels and speed up these wheels to get back onto track.
Okay. And how does it sense that?
The Adafruit IMU is a gyro sensor,
Gyro.
so it has a gyro sensor built into it.
He doesn't wear that during
No.
No.
That's just a show. Any other questions?
No. So the only thing missing right now is the camera?
So the camera's not on the robot right now. It's just the phone
Yeah.
that slides in. We're charging it right now, so that
Okay.
we're ready for our matches. And then also, what we left is, since we didn't get enough time to finish and it's our first qualifier, we have these 2 rails which are ready to, we have a cap haul mechanism that we designed in PTC Creo, and we just need to slide these on, and for our next qualifier, hopefully we'll be able to lift the cap.
Why did you choose the wheels?
So these are mechanical wheels, and one thing unique about them is they have omnidirectional movement. So we can move anywhere on a plane. So we can move sideways, we can move forward, backwards, diagonal, any direction. And these, out of all omnidirectional movement types of drivetrains, these have the most grip in the forward and backwards direction, so they have the most power.
And also in autonomous, since one of our goals was to press both of the beacons, we had to find an efficient way to get to the second beacon without too much motion.
Okay.
And so this was a quick way.
So just,
Yeah.
okay.
Great.
I don't have any more questions.
I think I'm good.
All right.
Thank you guys.
Good luck.
Thank you.
Good luck today.
You can send your cameraman back in.
Oh, yes.
Street.
Oh, yeah. Do you want me to get the camera?
Okay. Sorry. Thank you.
No worries.
Thank you.
It's hot in here.
Uh-huh.